In this video, we're up to our fifth lesson in Unit 3, and this lesson is on something called the chain rule. It's an incredibly useful rule for doing derivatives. It's actually pretty easy to figure out. It's actually harder to write down the instructions for the rule than it is to actually do it. So on-the-job training is sometimes the way to go. But we're going to take this first page just to get used to the idea of just notation for composite functions. These are functions inside functions, and then we'll see how the chain rule can allow us to find the derivative. So I just wanted to take a look at this this first pair of functions here and just look at how they're different. Okay, trying to figure out the order of operations for them. The first one, when it's written this way, actually is sine of x squared, and then the next one we would say it's sine of x squared. Right? It's kind of a difference in which operation you do first. For this first one, this first function, your first maneuver would be to square the x, and then once you have that value squared, then you would go and perform the sine value for that. Whereas the other function over here, the first thing that you would do is you would find sine x. Once you have that value, then you would go and square it. And so it's just an issue of which comes first and which comes second. By the way, and we'll talk about this bottom of the page, a little shorter way to write this, you can actually write that like that. Okay, so the issue of which comes first and which comes second comes back to the idea of what we call inside and outside functions. And so I've got this example here, this square root of this polynomial, x cubed plus 4x plus 1. And what's happening here is that the trinomial is happening first. We find its value, and then once we know the value for the trinomial, then we're going to root that entire answer. And so if you think about this, there's an outer function, which we're going to call f of x. And then inside, there's this internal one that's operating inside the larger function. And that one we're going to call u of x. So in my story here, I would say that the u of x, okay, it's written as a function of x because it's got x's in it. That would be this trinomial x cubed plus 4x plus 1. And then the outside function is the root that's happening to that. So it's operating on that whole trinomial. It's operating on u. And so you have this f of the u function, right? So this f of u is equal to the square root of u. And so I can see that the inside stuff is the trinomial. It happens first, and then the root happens later. The next one, the internal function, u of x here would be 4x plus root x. That's on the inside. And then operating outside of that, we have another function that's actually taking things up to the 8th power. So that would be that internal thing to the 8th power. This is going to happen a lot with trigonometry. Here I would say the inside function, the part that's happening first, is this operation 3x plus 2. And then once you know the value of 3x plus 2, then you can go and do the cosine of that 3x plus 2. So the f of u here would be cosine of u. All right, let's just play with this a little bit before we actually get to the calculus on the next page. So I've got a couple of functions here. One's a trinomial, the other is just a binomial. And we're going to just see what it looks like to put one function inside the other. So f of g of x, f is operating on the outside, and it's operating on the answer from g when you put x in. And so when I look at this, I'd say, okay, bigger outer picture is f. What does it do? It goes 2 plus whatever you put in goes to the 7th power, plus whatever you put in goes to the 3rd power. And now into that, we're going to go and put in not x's, but we're going to put in this 3 minus x, this g of x. So right here, and I guess I could write it like that, but instead I'm going to say, hey, okay, what does g actually do? Well, it goes 3 minus x, and then 3 minus x. So you can see the green stuff's happening first. The g of x occurs first. And then we're going to operate the f function on top of that. The other way around would be this g of f of x. This is one way to write it. Some people like to write it that way. This means exactly the same thing as this, right? No different from that. And so in this case, the outer function is g. Okay, so what does g do? Well, it goes 3 minus whatever you put in. Okay, well, what am I putting into g? I'm not putting x into it. I'm actually putting f of x into it. Well, there's f of x. So this one, this composite, would be like that. just doing things in the reverse order. They're not the same thing. So those processes of having one function inside the other, they don't reverse around. They don't commute, as we would say in the math world. Before we hit the next page, just a little reminder of our shortcut notation for doing higher powers of functions. If you see f with a square on it and then x after that, that actually means please go and find out what f of x is, and then after you're finished, when you have that value, then go and square it. Same thing with the one down underneath it. This means go and find the value for f of x first, come up with that value, then when you're done, go and raise it to the 5th power. Some specific examples from trigonometry, this tan squared x, that's how we could say it. That means go ahead, find out what tan of x is for the angle that you're working with. Then, when you're done, let's take that answer and square it. And the same thing with this cos 5th of x. We would actually find the cos of x first, come up with a value for that, and then we would take that answer when we would raise it to the 5th power. And that's true no matter what number you put up in that exponent, with one exception, the -1. That's just reserved for something different in math. We're going to talk about that in a couple of days. Okay, this means inverse function. It does not mean to raise it to a power of -1. It's not a reciprocal function, right? It doesn't mean 1 over it. Okay, same thing with this. Okay, this means inverse function. Something totally different. Okay, it's just not the same thing. It's not 1 over f of x. Okay, I think we're ready. I think we're ready to actually see how this chain rule works. And like I mentioned at the beginning of the video, it'd almost be better just to do on-the-job training and to skip the whole instructions right off the start. But we'll try it. Here are the instructions, and then it'll actually get, I think, much easier for you once we look at the examples. So the chain rule is for composites. I'll call that c of x, some composite function that has one function embedded in another. And as an example, we're going to do this square root of this trinomial, 4x cubed plus 2x squared plus x. So my outer function f, it's operating on this g, right? This answer that you get from g of x, right? So the same thing as that. And f is rooting things. And then the internal part, the g of x, that's actually doing that trinomial. Now we often like to use u for that internal function, just some historical thing that we've always done. So I guess in the story here, we could say, oh, this is u of x is 4x cubed plus 2x squared plus x. You're going to hear me talk about the blob, right? And I'm going to kind of look at this as just being a little blob of algebra. So I'm going to say, oh yeah, there's a little blob of algebra here. And the blob that's on the inside, very non-technical term, people call that b. That's like 4x cubed plus 2x squared plus x. I can just see that hunk of algebra, that blob of algebra just sitting inside this square root function. Here's the rule written 2 different ways. We'll do it with Leibniz's notation, and then we'll do it with Isaac Newton's notation. So Leibniz would say, okay, if you have to do a derivative of some composite with respect to x, we're first going to do the derivative of your composite with respect to that blob on the inside. Then we're going to multiply by the derivative of that blob with respect to the x that we should have done. So it's, you look at it and you go, oh, it's kind of like grade 8 fractions that are reducing. Yeah, it looks like that. It's not entirely what's going on here. This first fraction there, that's an instruction to do a derivative. So this is a derivative of the outside function, that outside pattern, with respect to, okay, thinking about the variable as being, that's what I mean by that, with respect to the blob. When we try an example out, you'll see how easy this actually is. And then the second derivative here, this is the derivative of the blob. So much easier to do than it is to write the instructions down for. Isaac Newton would say this: if you're trying to find the derivative of c is some sort of composite, then you need to go and find the derivative of c with u inside, with that blob inside, then multiply by u prime of x. Okay, enough of the technical stuff that doesn't make a lot of sense. Let's actually just try that out with this. trying to find the derivative of this composite function. Up until now, we have had no plan for doing this. So I would look at it and say, you know what, there's an outer function going on here that looks like this, right? We're rooting stuff. And then on the inside, there's this blob of algebra. Okay, so I'm actually picturing this story as kind of looking like this. There's just a blob of algebra, a hunk of algebra that's there, and then I'm trying to raise that blob up to the power of 1/2. So the chain rule says, if you're ready to do this, look at this first and just do a derivative pretending that blob is the variable. Kind of think of it as being like x to the 1/2. What would you do for that? Well, you'd pull the half down and then lower the half by 1. So I'm going to do exactly that. I'm going to go 1/2, and I'm going to just have the blob sitting in there, and then I'll go to the negative 1/2. So I'm just going to leave this blob. I won't do any calculus to it. Then right after that, then I'm going to go and multiply by the derivative of the blob. Blob prime. So it would actually look like this. Like right from the start, you jump right into this and say, okay, I can see this here. I'm ready to go. Here's what the derivative is going to look like. We're going to go with the pattern, 1/2, and then just leave the blob, 4x cubed plus 2, x squared plus x, all to the negative 1/2, times 12. X squared plus 4x plus 1. You might be like, where's that coming from? That's the derivative of 4x cubed plus 2x squared plus x. Key thing, when you're doing the first part, the first half of the chain rule, this part right here, just leave the blob alone. Don't actually do any derivative for that, okay? Then we multiply it by the derivative of the blob. Let's try a couple more out. I think after you've done 5 or 6, it'll start to feel much more comfortable. Okay, this first one on this page here, example 4, I'm seeing this blob of algebra inside there. So in my mind, I'm kind of picturing this thing as being pretty similar to, it's kind of like a y equals x squared, except it's just not as simple as x. It's got this blob in there. So the derivative, y prime, okay, the 2 comes down, leave the blob, do not touch it. Okay, just 3x squared plus 1, all to the first power, lowering that 2. Then I would go and multiply all of what I've just written down by the derivative of that blob, which would actually just be a 6x. Now you can tidy that up if you want. You can say, oh, okay, 2 times the 6 would be 12x, 3x squared plus 1 if you want. You can even distribute the brackets if you like. I want to show you another option, just another way you could have done this question, because we've done an example exactly this hard before and we didn't know the chain rule. You could rewrite the question and say, well, can't I actually think of that squaring as being 3x squared plus 1 times another 3x squared plus 1. For that matter, you could even FOIL the whole thing out right now and then do a derivative. But I'm going to take this just to the point of here and then do a product rule. So I could say, okay, the derivative, okay, here goes the product rule. Derivative of the first part, 6x, multiplied by the rest, 3x squared plus 1 just left alone. Then add, now reverse. Leave the first factor. And then the derivative of the second factor, 6x. Those are like terms, and if you collect them together, you get, guess what? 12x times 3x squared plus 1. So my point with that is there are, on some questions, there's so many different ways that you could jump into them. And no matter which way you look at it, as long as you approach it fairly, you're going to come up with an answer that's equivalent. But there will be times when the chain rule is the only way to go. This one here, okay, I've got this fraction with that binomial being cubed down in the denominator. If it was me, I would probably rewrite the question. I mean, I'm willing to do a quotient rule, but I'm never excited about it. So I might rethink this question as being x squared plus 1 all to the negative 3. It just looks a little nicer as far as calculus goes. Okay, the derivative. They've asked us to go and do a derivative of y. So whether they write it like this, which is what they're doing, saying please do a derivative of y, or whether they write it dy dx, it's all the same thing, or even y prime. Okay, all the same thing. Here we go. Definitely looking like there's a blob in there. Let's just leave that blob the way that it is, and we'll just work with that outer pattern. So we're going to have a negative 3 x squared plus 1 all to the negative 4. There, I just treated that yellow stuff as if it was x. But that's not totally finished. I cheated, right? I did a derivative with respect to that blob. So now I have to multiply everything that I just wrote down needs to get multiplied by the derivative of the inside, which would be 2x. Now, 99 times out of 100, I'd be happy just leaving it like that. But if you check the back of the textbook and you're like, okay, am I doing this right? Don't be shocked if they maybe tidied it up a little bit, put the 2 and the 3 together and called that negative 6x, all sitting on top of x squared plus 1 to the 4th. I'm not saying that that's any better. Sure, it's simpler, but you don't have to do that. Just be aware of the fact that the back of the textbook will probably look like that when you go to check your answer. So you can look at your work and go, yeah, my work here is equivalent to the answer in the back. We're good to go. Number 6 says, okay, find the derivative, then substitute in negative 1 for this expression here. We definitely have some blobs going on in here, right? There's a blob there, and a very similar looking, but slightly different blob here, actually. Okay, here we go. So, first derivative, f prime. We'll write it the Newtonian way. That looks like a yellow blob with a 1/3 exponent on it. That's the same thing as a cube root, right? So I'll just treat that as a blob with a 1/3, and I would say, okay, the 1/3 comes down. I'm going to have a 2x plus 3 all to the negative 2/3. But that was cheating. I just did a derivative with respect to the yellow blob. So I now have to multiply by the derivative of the yellow blob. I have to make sure all of this gets kicked with the derivative of that yellow blob. That would just be a 2. There, that's just been multiplied by the 2. Things are good. Moving on down the road, got a subtraction. Now, 5 blob cubed. Okay, so the 3 comes down, hits the 5, 15, leave the blob, all to the second power. Then multiply all of that by a 2. All right, there's the derivative. And they've said, well, would you be willing to do one more step? Can you go and figure out what the value of that would be when x is equal to negative 1, right? They've asked us to do this. Okay, sure. So we'll go 1/3. 2 times negative 1 would be a negative 2, plus 3 would be a 1, to the negative 2/3 times a 2 minus 15. Okay, and negative 1. 2 times negative 1 is negative 2. Add 1 is a negative 1. That's going to get squared, and then times a 2. Okay, what do we have here? Well, 1 to the negative 2/3. We're going to take a 1, flip it upside down, square it, cube root it. It's still a 1. So you're just going to have a 2/3 minus, that gets squared to be a positive 1, minus 30. Okay, so we're looking at going for thirds here. 2/3 minus 90/3. Okay, we're looking at negative 88/3. That would be my answer. You could do a decimal approximation if you want, but you would have to go to 4 decimal places. Number 7, capital F. Okay, some other function. Capital F is equal to f of, oh, there's a little internal function, g of x. And they're not even going to tell me what the algebra looks like. We're on like a need-to-know basis. And they're like, hey, you got to go and find f prime at 2. Oh, okay. All right, well, here's what I know. If I was going to try to find the derivative of capital F, okay, I'm doing d capital F dx. All right, well, I'm noticing that the outer function is this little f function, so I would need to do its derivative. But don't do a derivative of what's inside. Just leave it as just a g of x. Okay, leave the blob on the inside. But then you have to multiply by the derivative of that blob. That's what I would do. And if you could just tell me what the algebra was for g and for little f, I would go and do that for you. But they're not going to tell me. And now they're like, yeah, please go and evaluate this answer. F's derivative at 2. Or if you want, you can write it like this. Here's the Leibniz way. df dx figured out at x is equal to 2. Okay, time to put some 2's in here. We're going to have f prime of g of 2 times g prime of 2. Now it's time to start looking around for some help. G of 2 is 4, so this is like f prime of 4 times g prime of 2. F prime of 4 is 5. I'm glad they told me about that. I wouldn't have been able to do this question unless they told me that. And g prime of 2 is 3. Okay, and they just told me that there. Okay, well, here's my answer, 15. So you kind of look at it and go, well, why would they do that? Why would they make the question look like that? It's so that you can't use your graphing calculator. So you have to actually show that you're comfortable with the idea of the chain rule. That one was interesting. Now we're going to go and do some really big chain rule questions here. They're going to get really wide, so I have to kind of make my page wider here for this part. There we go. Example 8. See if you can find the derivative for that big thing. We can. It's not going to look pretty, but we can do it. We're definitely not going to simplify this thing. Okay, here goes. I'm going to do this derivative of f of x. So d f of x dx, doing a derivative. Okay, first thing I run into is this blob that's being all raised to the 5th power. Time for a chain rule. So I'm going to go 5 blob with no changes all to the 4th power. But that was cheating. I just treated that blob as if it was an x, and it's not. So I have to multiply everything that I just wrote down by the derivative of that turquoise blob. Okay, well, that's going to be a quotient rule. Never my favorite, but we can do it. Derivative of the top would be a 3, multiplied by the bottom left alone. Subtract, leave the top, multiplied by the derivative of the bottom, all divided by the bottom squared. Okay, well, that fraction bar makes it behave like a bracket, so that's good. Now, moving down the road, minus, because it says subtract sign, I've got the sign of a blob. So again, got a chain rule going on in there, right? There's a blob inside the sign. No problem. Let's just treat that pink blob like it's x for a second, and we would have said cos x. Okay, well, let's cos of that pink blob. That was cheating, though. I just treated that pink blob as if it was x, so I need to multiply everything that I just wrote down by the derivative of that blob, which would be a negative 12 x squared. That would be my derivative, and I would not be interested in cleaning it up. Just let it sit there. Number 9, we're going to do a derivative for this mess, and then when we're finished, we're going to go and substitute 4 in and see what it looks like. Okay, here goes. First of all, y prime of x. Let's not do it of 4 just yet. Okay, big picture, when I first glance at that, I'm seeing a quotient. I'm seeing something divided by something. So I know I'm going to be doing my quotient rule, and it's probably going to get a little ugly. So I'm going to make this nice and long. All right, derivative of the top. Ooh, I see a little blob in there. So as I go to do the derivative of the top, definitely going to have to do a chain rule for that. But it's all right, I'm ready. That's like 3x plus 4 to the half. So we'll have 1/2 3x plus 4 all to the negative 1/2. Now that was most of it, but now I have to multiply by the derivative of that blob, which would be a 3. Okay, that is the derivative of the top. Times the bottom, left alone. 2x squared minus x. Subtract, because you're doing a quotient rule, leave the top, just don't touch it, and then the derivative of the bottom. Well, that would be a 4x minus 1. And if I just leave it like that, it's not quite correct because this root needs to hit all of that 4x plus 1. So I need to get my order of operations right. And then we're going to divide all of that by the bottom squared. And now they're saying, well, you're not quite done. Now you need to go and actually evaluate that one time for 4. You can see why we're not going to simplify this, right? Like, why would you simplify it if you're just going to use it once? In goes the 4. Oh, this is going to be big. Okay, so we're going to have 1/2 times 3 times 4 is 12, add 4 is 16, all to the negative 1/2 times a 3, right? Times 2 times 4 squared, 2 times 16 is a 32, subtract 4, that's a 28, and then minus the root of 16 times 4 times 4 is 16, minus 1 is 15. No, this is not looking very pretty. All over the bottom squared. Well, that's a 28. That's getting squared. All right, well, let's see if we can make this happen here. Not a lot of room left. This 16 is getting square rooted and flipped upside down. So that's actually like a 4 that's flipped upside down. That's a 1/4. So we have a 1/4 multiplied by 1/2. That's an 1/8. And then we're going to multiply by 3. So like 3/8. And then times 28. Whew, that's a bit messy. The 28 is going to reduce with the 8. We're going to have a 14. I need some help here. I got lost. So 1/2 times 1/4 times 3 times 28. Okay, that's just 21/2. If I can say just. Needed a calculator to get there. And then this next part, 4 times 15. Okay, that's a 60. Okay, great. 60. And all that is sitting on top of 28 squared. 784. That's a complex fraction. That looks just messy. Let's clean it up by multiplying top and bottom by at least common denominator. Let's multiply top and bottom by a 2. That should make things a little more manageable. We will have 21 minus 120 all sitting on top of 1568. Okay, so that would be negative 99 all on top of 1568. I don't think that reduces. I'm going to check. 99 divided by 1568. It's going to ask my calculator, hey math, convert that to a fraction. Nope, that's as small as it gets. That's my answer for that one. So we don't do very many that are going to be that long and ugly, but we will do a couple. That one's definitely something that your calculator can help you out with. In contrast with this next one, where your calculator can't help you out. It's very similar to an example we did a page ago, where you've got this composite function, where this g of x blob is happening inside the f function, and they don't tell you the algebra. And then they're like, hey, you got to go and find this one derivative. Well, let's approach this the same way that we did the one a few examples ago. And we would have said, well, let's take a derivative of this h of x. So dh dx, that would be a chain rule. I've got this f of a blob. Well, let's just do the pattern that would come with that. And by the way, another way of writing dh dx is h prime of x, right? Same thing. So let's do the derivative of f. We'll do f prime, but don't touch the blob. Just leave it. And then you would go and multiply by the derivative of the blob. Okay. They're asking you to go and find g prime of 0. Now we did do one. I'm going to go back. We did one almost like this right here. And they were like, oh, hey, when you're done, can you go and find this thing that's all by itself on the left? And we knew everything else over here on the right. This one's close to that, except this time they're actually asking you for g prime of 0. So I'm looking at this g prime of x here thinking, hey, that could be helpful if I can make it look like g prime of 0. So let's just go and put in 0 to that, and then we would have this. We're going to go with 0 for x. So we'll have h prime at 0 would be f prime of g at 0 times g prime of 0. Okay, so I'm looking for that g prime of 0. Well, what do I know? I know that h prime of 0 is 4, so they've revealed this to me, right? They've said, oh, we're going to tell you that number's 4. Okay, let's keep going. F prime of, what's g of 0? Oh, we know that. That's actually a 1. Okay, so thanks for telling me that. Times, and then here's this one thing I'm looking for, right? I'm desperately trying to find, hey, what is g prime of 0? F prime of 1, they've told me that that's a 3. So they're giving me the answers here and saying, hey, that's 3. We can't tell you the algebra. It's a big secret. But we'll tell you that that works out to be a 3. And then here's the one thing that they do want you to go find. Okay, we're done. Looks like this thing that we're supposed to go and find, I don't even need to know what the algebra is. Just moving this around, that's going to have to be 4/3. So we did the chain rule in a question where you just can't use your graphing calculator to help you out. That's why they've worded it that way. The next one, you're going to sometimes see questions, they're in pretty much every single calculus textbook, where they actually express some function in terms of an internal function called u, and that's what's happening here. So y is equal to this thing called u squared minus 2u to the 5th. And then they're like, oh yeah, well, by the way, we'll tell you what u is. It's actually x minus root x. And then they want you to find the derivative of y with respect to x. Okay, fair enough. I think I can see how this thing is working here. What I'm going to try to avoid doing is this. Now, I know people will say, yeah, but it works. And it's like, sure, but you're missing the whole point of this question. You're being lazy, not buying into this whole chain rule idea the way that you can, just to get around saving a few seconds now, but it'll cost you so many more seconds later. Don't do this. Don't say, oh, I'm going to rewrite their question as y is equal to, now I know it's u squared, so something squared. And oh, what is it that's squared? I'm just going to go and substitute that stuff in, right? I'm just going to set this up ahead of time. And then I'll go and do a derivative because I'm good at that. Like, yeah, I know you're good at that, but this doesn't really pay off long term. You want to, on this question that's not too bad, figure out the game plan. That way you'll be ready to go. And here is the game plan. If you're trying to find dy dx, you can get there by going dy du and then du dx. That's the chain rule. Okay, this is my plan then. I'm going to say the derivative of y with respect to x is equal to, okay, what's the derivative of y with respect to u? I'm going to look right here and say, okay, u's are the variable. Yeah, sure they are. I can see them there. Okay, u's are the variable. Go ahead and do a derivative. That would be 2u minus 10u to the 4th. That is dy du. Now I'm going to go and multiply by this du dx. I'm going to put it right here. Okay, well, there's u doing a derivative of that with respect to x. I'm going to have a 1 minus, that's x to the 1/2. So 1/2 x to the negative 1/2. There, I'm done. Right? That's the way that they wanted you to buy into this question. Now they do have one last instruction. They're like, oh, we got to get you to go and evaluate this at a certain moment. Can you go and find dy dx at the moment when, and they've got an instruction there. They're saying, oh, can you do it at the moment when x is equal to 4? And the answer is sure. Yeah, I can do that at the moment when x is 4. No problem. Until I get to here. And I'm like, geez, what am I going to put in for this u? So you might need to just take a moment and say, hang on, I got to go find out what u is right now. So when x is equal to 4, what's u doing? U according to its pattern, it's x minus root x. It would be 4 minus root 4. That would be 4 minus 2. Okay, so u is equal to 2. So we're evaluating this when x is 4 and u is equal to 2. Great, here goes. So this would be, just looking at this blue stuff, 2 times 2 minus 10 times 2 to the 4th. Now here comes the orange stuff, times 1 minus 1/2. X's are 4. That's what I'd go with. Now, I can maybe get away with doing this in my head, maybe. 2 to the 4th is what, 16 times 10 is 160. 4 minus that, so we've got negative 156. And it's going to get multiplied by, what do we have here? 4 is getting rooted, that's a 2. Flipped upside down, that's a half. So that's a half, times another half is a quarter. 1 minus a quarter, 3/4. So it's 156 times 3/4. Now, okay, I cheated. I did that ahead of time. Did that on my calculator. It ends up being minus 117. Now, I get it. I know you might look back up here and say, hey, I can do this faster. I can take a derivative of that using the chain rule and then just put in x is equal to 4. I know you can do that, but that's not really buying into the intent of this question. So when you see these questions in the textbook, you do want to practice them this way, where you can say, hey, look, I'll do a derivative with respect to u, then the derivative of u with respect to x later. Last page. Another one of these deals where we're going to practice stuff just so that we can see what happens if you can't use your graphing calculator. Okay, just practicing the rules. So I don't know what the algebra for f and g and f prime and g prime are. I have no idea, but they've given me a table with a few numbers in it, and then they're like, okay, see if you can find some derivatives. And so you'll only come up with the right number if you know the rules. There's no real way to use your calculator to help you out. So if they said, all right, do this derivative and figure it out at x is equal to 2. Well, I'm noticing that there's this blob in there in that particular function, and the one beside it, well, I've got my highlighter going here. Seems to be a blob there. So here's what I would do. It's okay, you want me to do a derivative? Working across this here, I'll just do a derivative with respect to the blob, and I would have f prime of 2x. That says, yeah, just do the derivative, pretend 2x is x. But then right away, I would have to multiply by 2. Continuing on, plus g prime. Now, I don't know what the algebra is, so I can't show you the algebra for that, but they're like, yeah, that's okay. Just go ahead and work this out when x is equal to 2. So now we're going to go and evaluate this when x's are 2. So we're going to have f prime, well, 2 times 2 is 4, f prime of 4 times the 2, and then g prime of 2. So I sure hope we can find these in the table. F prime of 4, yeah, okay, x is 4, f prime there, okay, that's that number. And then g prime of 2, x is 2, g prime, negative 3. Yeah, okay, I can see those there. So this is like a 3 times a 2 plus a negative 3. Okay, I got the answer. My answer for that one is a 3. All right, the next one. So if we can just follow the pattern. Doing a derivative. Well, let's just pretend that g of x is like x. Let's just pretend it looks like that. It's like, oh, the derivative would be f prime of x. That's what the chain rule is all about. So we'll just leave this g when we first do our chain rule. And we'll say, okay, we're going to have f prime of the blob, right? Just leave that g of x. Don't touch it. Just leave that sitting there. Then you multiply by the derivative, g prime of x. And then they're saying, yeah, that's nice. It's neat that you could do that, that you knew the rules, but now can you go and put 2 in? See what you get. Sure. So we'll have f prime of g of 2 times g prime of 2. Okay, well, g of 2, just looking on the table, g of 2 is a 3. So we have f prime of 3, and then g prime of 2 is a negative 3. F prime of 3 is 2 pi. I don't know why, but it's 2 pi times a negative 3. Okay, I'm done. Negative 6 pi. I couldn't use my graphing calculator to get it to take a derivative for me. I needed to know the chain rule to get that to work. Okay, just a couple more, 3 more. Oh, this one's got a blob. Looks like F is the blob on the inside. It kind of strikes me as being like an X with a 1/2 on it for that root. So that's how I'm going to go and attack the chain rule here. I would say, all right, the half comes down, but just leave that blob, leave that f of x, all to the negative 1/2 times f prime of x. So notice I didn't touch that blob, right? I said, okay, that's blob to the half. All right, half comes down. And now again, there's no way that my calculator could have helped me out with that. I had to do it this way. And now I can go and evaluate this for 2. Just put the 2 in wherever I see x's. So I'm going to have 1/2 f of 2. Okay, let's just go and look and see what f of 2 is. Looks like it's 8 to the negative 1/2 multiplied by f prime of 2. Well, f prime of 2 is 1/3. Okay. Not super nice here. I've got a 1/2. This half on the exponent means I'm rooting it, and it's upside down. So 1 over root 8 times a 1/3. Okay, you know, there's nothing that says you have to write this in simple radical form. I would just write this as 1 over 6 root 8. Don't worry about the root 8 down there. It's not hurting anything. If you really want to worry about it, multiply top and bottom by root 2, and it'll get a bit better. D, what do we have here? You could do a quotient rule if you want. Personally, I don't like quotient rules, so I would rather think of it like this. This is g squared of x. Ooh, that's tricky. And it's all to the, it's all flipped upside down. Actually, let's go like this. Let's go g of x all to the negative 2. There, that's what's going on. It's been squared and flipped upside down. So now if I go and do my derivative, I'm going to treat this just like a blob for a minute. Just don't touch it. And we'll say, okay, it's negative 2 times that blob all to the negative 3, then multiply by the derivative of that blob. See, that's what your graphing calculator can't do, but we can do it. Now we're going to go and put in x is equal to 3. We'll just put it in here for x and in here and see what happens. Well, g of 3, just looking that up in the table, is a negative 4. And that's to the negative 3. And then g prime of 3 is a 5. Okay. This is going to be cubed and flipped upside down. We're going to have a negative 2, and then we're going to have this negative 4 cubed, and then a 5. That's a bit of a mess. The negatives will cancel. We have actually 4 negatives, so they're going to turn into a positive number. And then 4 cubed, what do we got there? 16 times another 4 is like a 64. Reducing with the 2. Okay, this is going to be 5/32. Yeah, you could use your calculator with your arithmetic, but you can't use your calculator to help you out with the chain rule. Whoa, this is interesting. This is like lots of composite stuff going on here. What's happening? Outer picture, there's this f function. Okay, what's going on inside this f function? What's going into that machine? There is a g of x, but it's getting squared. So the g is like really inside, like it's in here. And then after g happened, that answer got squared, and then that answer went into f, right? So it goes from the purple to the orange to the blue, working your way out. Okay, here goes. Derivative. For the moment, treat all of that like it's a blob, at least for the first move. And so I would end up with f prime, and then leave everything just the way it is. Okay, don't touch anything. So we'd have the squaring, and then you'd have the g of x. Okay, great. So that's happening with the derivative for f. Then I have to multiply by the derivative of what's inside. So I'm now only looking at this, trying to figure out what its derivative would be. Oh, okay. Well, let's do the orange pattern, and we'll treat the g of x like a blob. So we've got a chain rule hiding inside a chain rule. So that right there, that's going to be my blob for the next maneuver. And I'm going to say, okay, here we go. 2 times that g of x, all to the first power. And now I have to multiply by the derivative of what's inside that. So that would be g prime of x. All right, that's a lot of stuff. And then you'd have to work your way out. I don't even know if we have enough room. We're going to be putting 4 into this, okay, and see what happens. So what is g of 4? Looks like that's going to be a 1, and it's going to get squared. And then we're going to go and do f prime of that. Okay, looking down the road, g of 4 is a 1 to the first power, so that's 2 times 1. That's not too bad. Now g prime of 4 is a 2. Okay, f prime of, well, of a 1, really, right? So f prime of 1 is, what, 11.5? According to the rules there. So 11.5 times a 2 times a 2. That is going to be, what is that, 2346. So sure, your graphing calculator can help you out with the arithmetic, but it can't help you out with the chain rule. So that's why those questions like that actually exist. And that's the end of that lesson.